So it is known that 50% of male are left-handed. A sample of 100 MLB players had 25 left-handed players. Test the hypothesis that the proportion of left-handed players in MLB is different from the general population. As we know, left-handed players have some advantage when playing baseball, so they end up actually being good at baseball, so more people end up in the Major League Baseball and right-handed players, right? So you see something, and let's say we want to prove that statistically. So the general population, we know about 50% of male are left-handed, and then they bring in 100 random MLB players, and they find that 25 of them are left-handed. How do you test this? Well, we already know one way to test this, which is hypothesis testing of proportion. How do we do that? Well, see, if we were to do the hypothesis testing of proportion, testing of proportion, you would start by H0 being that the proportion for the MLB players is equal to 0.15. Right? With the alternative saying that I think it's different, right? So not equals to 15 will be the alternative hypothesis. And because we're not trying to show that it's bigger, it's just different. Because of that, so this is step one. Step two, you have a rejection region that's two-tailed. And let's just say we go with alpha equal to 0.05. Then it will be 1.96 here, negative 1.96 for the rejection region. That will be step two. And then for step three, we'll be using the test statistic as P minus, P hat minus P, where P hat is the proportion that we got. So from here we know that P hat is equal to 25 over 100, which is 0.25, right? So from there we have P hat 0.25 minus 0.15 divided by square root of, the variance is PQ for a Bernoulli trial, and because you have n number of these, you take that. So you compute that, and then whatever that is, the difference will be 0.1 times 10, it will be 1 divided by, I'm not so sure what this value would be. And then after this, you figure out whether it should be rejected or fail to reject. It's either one of the two. Okay? So that's how you do the hypothesis testing of proportion. Now let me show you another way to view the same question. Now you might be asking, if we already know how to do it in one way, why bother doing the other way? Well, the thing is, the chi-square test can be used for cases where you don't have just two kinds of proportions. You might have something like, in a certain species, we know that let's say one has, so for a certain race, we know that some proportions have eyes that are blue, some are brown, and some are green. And then if you know the proportion, and then you go to another region, and you want to test whether this goodness of fit does work, you can still use chi-square test for goodness of fit, whereas if you have more than two categories, then you can't use this, right? I'm only showing you this one so that I can compare the two, okay? All right, so now let me explain what chi-square test for goodness of fit is. For the goodness of fit, what you do is Again, your hypothesis is that your proportion is according to what's expected. So you will have left-handed as 0.15% of the population, and right-handed would be 0.85. Okay, that should be your hypothesis, and the alternative hypothesis is that the proportion is wrong. Even if you account for the fact that there's some randomness in this sample, there will be very low probability that the proportion will be this much different. Okay, so that's the alternative. And in this case, number 2, when you think about the rejection region, what you do is you have to first determine the degrees of freedom, because we have to use the chi-square distribution. So you have to first determine the degrees of freedom. And degrees of freedom for goodness of fit is always number of categories minus 1. Okay? So since right now we have left-handed and right-handed, there are 2 categories. So it's 2 minus 1 equals to 1. So you have just 1 degrees of freedom. And you've seen the chi-square distribution for degree 1. It looks something like this, right? It started somewhere high here and then did that. And what we are going to calculate is how off our sample is from the ideal case. So it will be, we'll be looking at some value here where this value would have, this rejection critical number, I'll say chi alpha. This chi alpha will have the property that the right side would be 0.05 area. Okay? So, do I have that? Oh. Okay. I forgot to print out the chi-square degrees of freedom critical value. So if you have your phone, please look up chi-square table. And somebody tell me what the critical value for degrees of freedom 1 with 0.05 significance level. Can you find it? Well, images. Okay. So for degrees of freedom 1, okay, the critical value is 3.841. Okay. So we know that this is 3.841. Okay. Now is the important part. What is the test statistic here? The chi-squared test statistic is going to be computed by the sum of the observed minus expected squared, and you divide it by expected. That's our chi-square test statistic. Okay, let's try to see what we have for each. First, the left-handed category. What's our observed? 25 is the observed, right? What was the expected? 15, because 15% should be left-handed. So minus 15 squared, then you divide it by 15, right? Plus, okay. Now let's go to the right-handed category. What's the observed? 75 were right-handed. What was the expected? 85 squared, and you divide it by 85. Okay. Now tell me what you get here. That's 100 divided by 15. 20 divided by 3. So 6.66, 67. Is that right? Okay. Plus, this is 100 divided by 85, so 1.2? 1.15? I don't know. What do you get? 100 divided by 85. Huh?
1.176.
1.176. Okay, 1.18. Okay. So you have here the sum of these two is 7.85. Okay. Does this fall in the rejection region? Yes, yes, it does. It falls right here. 7.85. So what's our conclusion? Number 4. Reject or accept? Reject H0. Which means that we have proven with 0.05 significance level that the proportion of left-handed people in the MLB is quite different from the general population. That's what we proved. Now, just out of curiosity, let's go back to this one. How do we do this one? This would be P hat is our observed probability, which is 0.25, minus the population probability, which is 0.15, square root, P is 0.15, Q is, what's Q? 0.85, 1 minus 0.15, 0.85, divided by 100. Okay, can somebody do this for me? Let me see, that's 0.1 times 10. I don't know.
2.8.
2 point what?
2.80.
2.80? Okay. Alright, so again, with this, 2.8 is in the rejection region, so you get the same result. We reject the null, and using this method, you've shown the same. Okay? Now, here's something else I want you to do. Take this value and square it. What do you get? What's the square of 2.8?
Is it going to be 7.87?
It'll be this one. You get 7.8. Okay? Now that's expected because what's the meaning of the chi-squared again? 1 degrees of freedom is simply square of the normal distribution, right? We know that if I do this test statistic, then Z follows N01, standard normal distribution. And the definition of chi-squared is that if you square this, you get the chi-squared distribution. So having a two-tailed test in this format is exactly same as the chi-squared test for degree 1. That's why this works, okay? Now, if you're still not convinced, I can actually give you a proof. So let me give you a quick proof of why either methods will give you the same conclusion. So, let's see. I want to show that if you do Z equals to P hat minus P over square root of PQ over N, and you square both sides, you get the same exact thing that we had for the chi-square. Okay. And then I want to show that by working on both ends. So let's start with this one. What is this? This is p hat minus p squared over square gets rid of the square root, so it's pq over n. And you have a fraction inside fraction, so you can simplify a fraction inside a fraction by multiplying top and bottom by n, which cancels this n in the denominator, which gives you n times p hat minus p squared over pq. Now, I look at this for a while and then say, well, you know what? If you do n times p hat, that's 25 in our context, right? N is 100. 100 times 0.25 gives you 25, which is the observed quantity, right? And if you do n times p, that's 100 times 0.15, which is 15, which is the expected quantity. So if you want this to look more like that, I want this to go inside. But to go inside, you need n squared, right? So I'm going to multiply another n top and bottom. So I'm going to multiply n top and bottom so that this is now equal to n squared, which goes inside. So you get np hat minus np squared over npq. Okay, this still doesn't look like this other chi-squared, so let's work on that one. Now let's work with chi-squared. Chi-squared is, first of all, what is the observed? As I said, observed is n times p hat, right? This gives you the observed quantity minus what is the expected quantity? np. You square that, and you're dividing by np. On the other hand, what is the observed quantity of the other guy? That's n times q hat, right? Yeah, it's q hat minus n times just q. Q is the expected. This is the observed, right? This q hat is the observed proportion. This is the expected proportion, right? Divided by same number, nq. All right, now it's more hopeful because they look very similar, right? So what we're going to do now is, I want to make the denominator at least look like npq. So I'm going to multiply q to the first guy, and I'm going to multiply p to the second guy. Okay? I'm just going to erase this other one because we've already finished the work. Okay. And I'm happy with the first term. I'm just not going to touch this at all. And in the second term, there's a term that I'm not happy with. This q hat and q, those don't appear in the original one, right? Well, q does get used somewhere, so that's okay. But q hat never appears, so that q hat must not be used. Instead of q hat, we should use what? Q hat is same as 1 minus p hat. So you put n times 1 minus p hat minus nq. Right. Oh, that's also 1 minus p, right? Isn't that right? Okay, so I just replace both of the q hat and q by just this, okay? Squared times p over npq. But, you know, if you multiply them out, n minus n cancels each other, right? And here, this thing becomes negative np hat plus, minus is plus np squared. Now, we wish this was plus and that was minus, so that's same thing as that one. But there's nothing to worry about. It is equal to this plus this minus because it's squared. Right? So square allows you to change this to plus and then this to minus because they're negatives of each other. So if you do that, you end up with np hat minus np squared q over NPQ plus NP hat minus NP squared times P over NPQ. And now you see that these are exactly the same, right? So you can factor that part out. If you factor them out, what do you end up with?
Plus P.
N P plus Q plus P, right? That's what you get. Q plus P. What is Q plus P? 1. So this is just 1. So what did we just prove? This is indeed same as this other one. Right? So that's why it will always be true. I've just shown you that when you just have two categories, it doesn't matter if you use the test of the proportion or you use the chi-square goodness of fit. Is that okay?